Lesson 13 looks at linear regression. Linear regression is used for examining the relationship between two variables. You have an input variable, the explanatory variable. This is your independent variable. And I remember that this is x because it starts out as explanatory. And we also have a y value that's linked to it. The y value is called the response variable or the output or the dependent variable. Any of those phrases mean the same thing. So assuming we set this up correctly, linear regression allows us to make predictions about what should happen given a limited amount of information. So here I have some years for the Olympic and the finishing times for the winning times for the 100-meter Olympic race in seconds. So if I wanted to graph this thing, I would have a y-axis or a response variable of the winning time for the 100-meter, and this is in seconds. So this is time in seconds. And for the x-axis here, my explanatory variable is equal to the year. And any good graph has a title, so my title for this thing will be winning times for the 100-meter Olympic. So I have the years from 1980 up to 2012. I'm wondering if I can use this information to kind of predict what winning time should be in, for example, the 2021 Olympics. So using this limited amount of information, I'm going to come up with a scatter plot. So I'm just going to dot all these things and see what it looks like. And then I'm going to describe the scatter plot if the times are getting faster, if they're getting slower, if the line is increasing, if it's decreasing, if it looks like a parabola or an exponential, whatever the case may be. And I've cheated a little bit in that I have all these values copied and pasted, and I'm going to go into GeoGebra here, and I'm just going to come up with a quick graph to see what this looks like. So here's what I do in GeoGebra to come up with a scatter plot. I open GeoGebra, great. I go into the option for spreadsheet. In the X list, I'm going to type in all of the years, 1980, 1984, 1996, and so on. And for the Y values, I'm going to type in the winning times. If you're following in at home, you might want to pause the video here and take a second to type in these numbers. Assuming you've typed in the numbers, your next step is going to be click in like the middle of the block and just drag to highlight all of those values. After you've highlighted the values, you're going to click the thing that looks like a histogram, and I'm trying to come up with a scatter plot that's going to look like a whole bunch of dots in space. This is looking at paired data, and I'm using paired data to make predictions about the future. So this almost has a matched pair kind of feel to it. So this is kind of sort of like a t-test-ish thing. And when I graph this, I notice that my scatter plot does something kind of like this. I'm going to draw just a super rough sketch of this thing. And in addition to this, down where it says regression model, I can do a whole bunch of different things here and see which one of these kind of goes through the dots as best as possible. So this is what a line looks like. I'm going to try an exponential. Exponential doesn't look that much different than a line. If it doesn't look that much different and one of these equations is easier for you to work with, for example, if it's easier for you to do algebra with lines instead of exponentials, then use lines. Let me try a sine curve. Won't even let me do a sine curve. Okay, that's fine. Logistic. Okay, so out of all of these things so far, it seems like line might be my best fit there. So I have a scatter plot, I have a line, And you may have noticed it actually gives me the equation of the line. So I'm going to write this down right now in my packet. I'll come back to the packet. But I have y equals negative 0.016x plus 41.7926. I already have the equation for the line of best fit. Another thing I want to note is if I go up here to the top where I see this little sigma x symbol, when I type this, this gives me a whole lot of information. Interesting enough, I see this SSE, sum of squares of the air, that looks really, really similar to what's going on with ANOVA. And in actuality, linear regression and ANOVA will end up using almost the same model when it comes down to things. The only other numbers that I'm going to pull from this bank, and I don't know what these mean just yet. I have an R of negative 0.9368, and I have an R squared of 0.8777. I'm going to return to the overhead where I've written down this information. And let's proceed to try to use this to make some predictions and figure out exactly what GeoGebra has just told us, because it's told us a considerable amount. So I am switching back to the packet. Great. And my rough sketch of my scatter plot was something like this. If I squint my eyes a little bit and try to see what's going on, I think this almost looks like a line. The equation of this line appears to be y equals negative 0.016x plus 41.7926. It's a little hard to read there in the red, but I have the same line written down there in the bottom. Just a reminder, when I'm talking about x values, I am talking about the year. When I'm talking about y values, I'm talking about the time in seconds. So let's describe this scatter plot now using some words. Well, first off, shape. This kind of looks like a line to me. Direction. I would say this line is decreasing. So as time goes on, the finishing times for the 100-meter run appear to be getting smaller. Now, at some point, it's probably going to cap out with like a physical limitation of the human body, but currently it still has sort of this linear feel to it. And finally, I have fit. And fit is how much does it look like the indicated shape. So shape is telling me if you squint your eyes, does it look like a line, a parabola, an exponential, whatever you think you see. This is like looking at clouds, and I can see a line and you can see a rabbit. It doesn't make one of us right. We just have to be consistent with whatever our choice is. So I said line. Line was decreasing. And I would say, kind of glancing at this, it looked reasonably close to a line. So I would say that this was a fairly good fit. I didn't have to squint my eyes that much to have that look like a line. If it just looked like a cloud and there was no coherent thing holding that together, I might disagree when it comes to the fit. Now, I have also this r and this r squared that my calculator gave me. I want to try to figure out what those things are telling me, but just as a pre-note, r and r squared, these are both related to the fit and the direction. So something about r will tell me if my line is going up or down. Something about both r and r squared will tell me something about fit. We're going to return to this line to make predictions. So I'm keeping this to the side. I'm not taking this too far away today. But let's look at what's going on with r, and let's look at what's going on for r squared. So next 2 pages, I'm going to have a page where I'm talking about r. This is called the correlation coefficient. And I'm going to look at r squared on the next page. This has something to do with the percentage fit. And let's just jump straight into it. So we call the input the explanatory variable. Again, this is the thing we control. The output is the response variable. And to determine how related things are, I use the term correlation to describe the relationship between two variables. And correlation is a number r, and r always has the following properties. R is between -1 and +1. So making a little bit of a number line, the smallest r can ever be is -1. The biggest r can ever be is +1. And in the middle I have 0. If your r is greater than 0, that tells you that your data plot is increasing. So a positive r would have a scatter plot going up. A negative r value tells you that your scatter plot is going down. If your r is close to +1, that tells you it's almost a perfect fit going upwards. It's like 100% aligned going up. If your r is close to -1, that's almost a perfect fit going downwards. So both -1, this is a really good fit, and +1 are really good fits. So you might be wondering, well, what's something bad? Well, if I have a correlation of 0, this tells me that the two variables are not related. So I have 0 represents something that doesn't look like a line at all. There's no correlation. I think of this like a reverse Oreo. So the outsides are good and the inside is bad here. So -1 and +1, those are really strong R values. Anything close to 0 is a pretty weak R value. So I'm going to give you a couple of scatter plots. And we're going to do a little bit of matching. So suppose I have these 4 scatter plots, and I have R values that match up with these things as -0.02, -0.98, +0.88, and +0.72. If you are following along at home, try pausing the video here and seeing if you can do the matchup to see how close you are for these variables and figuring out which R matches up with which graph. I'll give you a second to pause and try that out. If you're joining us and you're doing the matchy-matchy, I would say one of these things is going to clearly be this -0.02, and I would say that's this one. Notice how this cloud kind of goes downward, so maybe there's a little bit of a negative trend to it, but for the most part, it's just a cloud of points and there's no clear relation. It's really close to 0. Likewise, I would say 0.88 and 0.72, these are both positive slopes. These have to be correlated with the two graphs that are going upward. So I have 0.88 and 0.72 describing these two graphs. How do I know which one is which? Well, whichever one looks more like a line will have the better R value of 0.88. This might be a steeper line, but R doesn't care anything about the steepness. It just cares about how close it looks to the indicated form. So for example, this looks almost perfectly like a line, so this should be really close to either +1 or -1. But it's going downwards, so I know that this should be really, really close to -1. -0.98 seems pretty reasonable. There's a formula for coming up with R, but we can use technology to come up with R as well. And as a reminder, when we did this just a moment ago in GeoGebra, I got -0.9368. This is telling me a couple things. First thing this is telling me is that my line has a downward trend. it has a negative slope. The other thing it's telling me is this is pretty close to -1, so I am also noticing that this would be a fairly good fit. So should I use that line to make predictions about winning times for future Olympics? My prediction should be reasonable at least for a while. In order to find this using a calculator instead, in the TI-89, go Apps and Stat List Editor, and then type in list 1 all of your X values, and in list 2 type in all of your Y values. And I'm doing this for that data that I had on the first page, the data for all of the years and winning times. And after I look at the years and the winning times, next thing I'm going to do is I'm going to go up to F4 for calculate. So I hit F4 for calculate. And now I'm going to choose the option for regression. And either one of the first two options is fine. I'm going to choose linear regression, and I'm going to hit enter. Now, my TI-89 is a little bit hard to read, but I ended up getting an R of -0.016, same thing I got in GeoGebra. I got a B of 41.7926, again the same as GeoGebra, and it gave me both an R and an R squared, matching up with the same values as before. So if you have a TI-89, the process is Stat List Editor. You type in your data in list 1 and list 2, and then you calculate a regression line that looks like AX plus B. I'm going to do that in my TI-84 as well. So stat, edit, and then I type in all of those years. I have those years typed in already. Next, I'm going to go stat, calculate, and I'm going to choose the option that looks like linear regression AX plus B. I have my X values are in list 1, my Y values are in list 2. So I'm going to go down to calculate, and it gives me A, B, R squared, and R. A is the slope, it's next to the X value. B is my Y-intercept, that's 42.764. R is telling me if the line is going up or down, and R squared is telling me about the fit there. So I've got my data typed into my calculator. I'm going to move on to the next step of this process. My R was -0.9368. It gave me some additional information besides that, but at least I have my R to know if my line is going up or down. Part of the problem is, though, that if I'm wondering if this thing is good fit or not a good fit, having both -1 and +1 being good values can be a little bit confusing. So to deal with the sign issues, we're going to try to square everything, and let's see what we get. So if I square my R, I get R squared. Now this is going to look a little funky, but the notation for this is actually a capital R squared, but in your head you should just be thinking, I'm taking my R value, like my -0.9368, and I'm going to square this, and let's see what number it gives me. When I do this, I get, just like my calculator told me and GeoGebra told me, 0.8777 or so. Great. This number is the percent of variation accounted for by my model. So R squared is always between 0%, this is telling me that it does not look linear at all, to 1, 1 would be something that is perfectly linear. If r squared is a percentage of good stuff, then 1 minus r squared is the percentage of bad stuff. So in other words, it looks kind of 87.77% like a line. That means 12.23% of the variation is unaccounted for, and that could be due to just sampling error, or there could be some lurking variable that I'm not aware of. For example, maybe shoes have gotten better in such a way that it affects the Olympic times, but shoes were only available, this new style of shoes, after a certain year. So there might be some sort of bias that this is actually detecting for me. This is my personal feeling. I feel like if you have an 85% or higher for your fit, that's a pretty good fit. If you have between a 75 and an 85, I think that's an okay fit. And if you have less than a 75, I consider that a poor fit. I'm just thinking of how I would feel about grades if I got certain grades on a test. If I got an 85 or higher, I would feel pretty good about that. If I got 75 through 85 on an exam, I would feel okay about that. I wouldn't put it on my fridge or anything. If I got 75% or less, I probably would want to study harder for that next exam. R squared was 87.77%. That's pretty good. That tells me when I make predictions, those should be reasonable predictions. Now, when I did stat calc, whether that be F4 calc or just calc in your TI-84, and then linear regression, AX plus B, this gave me a line of Y equals AX plus B, just the way it was written down, A, X, and then the B. My calculator gave me an A of negative 0.016 X plus, and for a B, it gave me 41.793. This is exactly the same thing that we got in GeoGebra as well. And the nice part of this is we can make predictions using this line to try to figure out what's going on for certain years. So for example, what would the 100-meter time be in the year 2016 if I'm using this equation? Well, Y equals, I'm given the year X, and I want to predict what my Y value should be. So I have Y equals, I'm going to take my A, X plus B formula, and I'm going to plug in my year 2016. And let's see what this spits out for us. So I'm not doing anything special except plugging something into a line. But the result itself is kind of special, because now I've predicted that the time should be 9.537 seconds for that winning time. And in actuality, the winning time in 2016 was 9.81 seconds. So when I'm looking at this, I'm thinking this is an okay prediction. And one of the reasons why I think this is probably an okay prediction is 2016 isn't that far away from the data that I already have. So this is extrapolation. This is outside of my data set for years. But it is barely extrapolation. It's just sort of the next year in the sequence. Let's make a prediction for what the time would be in the year 2000, okay? Well, same thing. But I'm plugging in 2000. So same thing, but I'm changing the x value. This gave me 9.793 seconds. And if I look back at my table, in the year 2000, the actual y value was 9.87 seconds. So that's really close as well. In fact, kind of looking at these two things, this seems like this is a closer prediction than this prediction. One of the reasons for this is the year 2000 is inside of my data set, and whenever I make inside predictions, whenever I do interpolation, that's an inside the data set prediction, those tend to be stronger guesses. Extrapolation in the extreme, things can break down considerably. So let's consider the year 3000. This is outside, it's extra, it's on top of. And I'm making a prediction for the year 3000. 3000 is so far away from my data set here that I'm anticipating that I'll have a almost nonsensical answer. But let's type it in all the same and see. I got negative 6.207 seconds. So in the year 3000, they're going so fast that they're going backwards on time. That doesn't make any sense in the context of the problem. In general, extrapolation, this is the weaker type of prediction. But even though it's weaker, it's actually more interesting too. I'm allowed to predict the future. That's way more interesting than me trying to figure out what has already happened in the present. Because in a lot of situations, I can just do the research and find that out for myself. So I'm using this linear regression to try to predict what's happening next. I'm going to keep this page close to me because I'm going to return to this after going over the next page. And I'm going to fix some of the notation issues I have here, because I'm a little bit worried that I'm using the letter Y both for what it actually was in the year 2000 and for the prediction. I want to be able to tell these Y's apart so I can quickly see some symbol that says, hey, I'm guessing for what it should be in this year. So that way if someone says Y equals, I'm not like, was it really that? Or did you guess that it was that? So here's the idea of what's going on. In previous math courses, you may have seen something like y equals mx plus b. M is your slope. B is your y-intercept. So I have some cloud of points. And my goal is to come up with a line that goes through these points as best as possible. Now, when I'm looking at all these little points, these are real data values. They represented certain times in certain years. So the data is an actual y value. So this right here, this is a true y. This is something that has happened. In contrast, when I'm looking at the line is a predicted time for what that should be for the 100-meter race. So to say it's a predicted y value, the notation I use is y hat. I'm putting a hat over anything when I'm making a guess. So going back to our previous equation, when I'm looking at a line, all of these lines are trying to guess what should happen for the future, or any year for that matter. And I put a hat to say I'm guessing what it should be. In contrast, the actual value I'm going to write without a hat. I'm just going to call a y. So for example, in the year 2000, when I looked at the data, the Y value was 9.87. In contrast, when I plugged in 2000 into the equation, I got 9.793 as my predicted value. So Y is coming from the data, Y hat, this is the value from the line. And there's some error that happens between what I am actually getting and what I'm anticipating I get. And this amount that I'm off is called the residual. So what's going on is I have my predicted Y value and my actual Y value. And my error, I can visually see as the amount of distance I am away from the line. So that's one residual. This is another error I have. That's another residual. This is another error. This is another error. This is another. My residual is the distance that my points are away from my line. And my least squares line makes these errors as small as possible on average. So in previous math courses, you may have seen y equals mx plus b for your equations of lines. Now we're going to have to use y hat to say, hey, I'm making a prediction. And that prediction could be wrong. There could be some residual linked to it. Now, you're actually not making just one prediction. You're kind of predicting the whole line. You're going to make a prediction for the slope. I have B1 as the predicted slope. And you have plus B0. B0, this is your predicted Y-intercept. I'm predicting kind of everything that goes into the equation of my line. So in stats, my equation is y hat equals b1x plus b0. This guess what should happen for the future. We made such a guess for the year 2000. Let's see what our error looks like for that year. And I'm just going to take the value that I had from the data, and I'm going to subtract the value that I got from the line. So I'm going to do 9.87, and I'm going to subtract the predicted value of 9.793, and let's see what our residual or error amount is like for this particular year. And when I do that, I get a residual of 0.077 or so, up to a little bit of round off. Now, something interesting that your TI-89 does, if you have a TI-89, is as soon as you finish doing your regression, it spits out an extra column, and that extra column says resid. So these are actual residuals for all of the indicated years. I'm going to write out what we had for our year and what our residual or error amount was like for that given year using my calculator. So my years were 1980, 1984, 1996, the year 2000, 2004, 2008, and finally 2012. Now you can do the subtraction and find each of these residuals one at a time. I am just using my calculator to come up with this. So I have something like 0.0927 in 1980. I have negative 0.1034 For 1996, I have negative 0.0617. For the year 2000, I have 0.03223. So I had a little bit of round off error earlier. This is actually much more accurate with the calculator because it's using more digits. I have for the year 2004, 0.07614. I have negative 0.0199 for the year 2008. And in 2012, I had negative 0.0160 or so. And looking at my line, this is the amount of error I have each in the predictions. The most error I ever had was off by like 1/10 of a second. So this was a really, really good model for predictions, actually. My errors were small. My R squared was close to 100%. My R squared was equal to, when we did this earlier, 87.77%. So I was expecting small errors, and I got small errors. Now, I want you to take a moment and only look at the residual part of this list, and I'd like you to determine what the standard deviation is for the errors and what the average is for the errors. I'm going to give you a second to pause and try that out on your own. Let's see what you get for those values. So if you're doing 1var stats in your calculator, that's totally fine. You could also do this using GeoGebra, or you can calculate it by hand. I used my calculator, and I found an average of 1.19, negative 1.19 times 10 to the negative 12th. In other words, I ended up getting an average error of 0. And this kind of makes sense. This is the whole point of the line. It's supposed to minimize the total average error. Sometimes I'm going to overestimate, sometimes I'm going to underestimate, but on average, I have 0 error. My standard deviation for this was 0.0739 or so. So I expect my average error to be around 0, give or take that standard deviation for the errors. So here's sort of a picture for what's going on. I have some sort of a scatter plot, and I have my line going through this scatter plot. When I'm talking about the distribution for the errors, I'm saying close to the line. I'm expecting my values to be reasonably close to that line. So the most likely spots are going to be towards the center of the line, and it's going to get less likely going up or down. So I'm thinking of this sort of as a probability model. It's really likely close to the center, considerably less likely as you go away from that curve. And this is wherever you are on the distribution. So it's really likely towards the center, less likely above and below. It is really likely in the center, less likely as you go down and above. So it's almost like I have a tunnel of these normal distributions. So I expect my errors to have a normal distribution-like shape. Bit of a problem though, I wouldn't say that these things are normally distributed because we have S. So when I'm working with something that looks normal but I have S instead of sigma, I'm going to use the T distribution. And the T distribution is going to have some degree of freedom. We'll circle back to that. It will have some average of the errors and some standard deviation for those errors. So our errors should have a normal distribution, but since it's not sigma, it's S, I'm using T instead. And the error should be really close to 0, give or take whatever number we found. So I'm expecting close to 0, give or take 0.07. So that's kind of the amount I'm adding above and below the line, where I'm trying to figure out where points should go. As far as the degree of freedom is concerned, degree of freedom is equal to the number of points minus the number of variables that we're predicting. When we were looking at lines, we had y equals mx plus b. There were two things that we had to guess here. I had to guess my slope, and I had to guess my y-intercept. I'm working with two variables. I'm working with x and y. So previously, I just had k minus 1, but now that I'm in multiple dimensions, my degree of freedom is going to end up being k minus 2. Here's what this means. If I want to make predictions using this line, I could actually make confidence intervals for each of these values to try to figure out what's going above and below. That's going to have a t distribution with a k minus 2 degree of freedom. I expect no error, and any error that I do have should follow the standard deviation for the residuals. This has been a review of all the material that we needed to know kind of before entering 244, where I start to look at this stuff with a critical lens towards making predictions. So I'm going to flip the page and I'm going to make a couple doodles, and then I'm going to move on to sort of the next step here. So I expect my errors to have a t distribution with k minus 2 degrees of freedom. I expect my standard errors to have the formula where I have my individual errors minus the center squared, and I'm dividing this by the degree of freedom, k minus 2. This formula I'm not going to test you on directly, but I do use this formula for other things. Let me show you what those other things are. So again, I'm kind of drawing this corridor of points where I have a line, and this line is wiggling inside of essentially a tunnel where all of these errors follow a t distribution with k minus 2 degrees of freedom, a center of 0, so this is describing these mounds, and some standard error for how those things vary. My line looks like y hat equals b1x plus b0. My y hat is my predicted y value. My b1 is my predicted slope. And my b0, this is my predicted y-intercept. Because if somehow I added another point, say I added a point here, my line would shift because of that point. So maybe I'd end up with a new regression line of something like this if I were to add that extra point. So my line varies a lot as I add and decrease data. It kind of wiggles around inside of this corridor here. So when I say predicted slope, that's because the slope can still be variable as I get more information. My y-intercept can also change as I get more information. Should I have complete information, then the actual slope, if I knew everything, I'm going to call capital B1, I'm going to call it beta 1. And the actual y-intercept, if I knew everything about the problem, I'm calling beta 0. So I am using this B1 that I got from a calculator, my slope, to predict what's going on with B1. And if I'm making predictions, then I can easily have a hypothesis test related to the slope, and I could create a confidence interval for all possible values of our slope. In other words, I can use this sample information B1 to predict what should happen with my population value beta 1. This was the sort of theme of the entire course, is I use sample information to predict what should happen for a population. I could do the same thing for my y-intercept. So I am using my y-intercept that I got from my calculator to predict the population y-intercept beta 0. And I can do an h-test and a confidence interval for my y-intercept to see where that thing should end up, as well as the slope. So I'm taking my 243 material of just coming up with a line, and now I'm going to try to use this material to kind of put it in a 244 lens, where I make predictions about where this should really be, given even just a tiny bit more information. So I'm going to flip the page over, and we're just going to go through a lot of this process together. But this is just an overview of what we're dealing with. B1 is my predicted slope. The actual slope is beta 1. B0 is my actual y-intercept, and B0 is prediction for what that beta 0 should be. There's a lot going on, but we're going to use technology to get to it. So we're in theory for just a tiny bit longer. Stay with me, and then let's see what this looks like in context of some problems. So error was unavoidable, and we're making two big predictions. We predict a value for the slope, B1, when the actual slope is beta 1. We predict a value for the starting y-intercept using B0, when the actual starting value might be unknown yet, beta 0. We've lost 2 degrees of freedom, so our degree of freedom is k minus 2 because of these two unknown factors, the slope and the y-intercept. Both of these predictions are affected by our residuals. Our residuals, that little tunnel, tells us how much that line's allowed to wiggle. Since this followed a t-distribution, both the slope and the y-intercept will be test related to t-scores. So my assumptions for doing any sort of inference for these unknowns, I'll have random, I'll have independence, or the 10% rule as a backup, so the usual. I need to have a large sample size. My data should look like a line, because if it doesn't look like a line, then I shouldn't come up with a line. That's a no-brainer. I need to make sure that when I graph my data, that it kind of stays as a line, so I could be making pretty good predictions. If I had something like this where it just kind of got crazy at the end, I wouldn't feel great about making predictions at all for that. My tunnels would not be the same size. I need to have consistent spread throughout in order to use this type of prediction. So I need to make sure that my line stays relatively clumped and smooth together. That's requiring my errors to look normal. Otherwise, I can't actually use this model to make predictions. Okay, there's a lot going on there. Fine. I want to look back at the picture for a second, and then I'm going to show you how to do a test. This one test is the most important part of linear regression, besides the line itself. when I'm trying to figure out what the most important factor is for these Olympic times, it's not necessarily where the time started in, say, the year 1984, but it's how much that time changes from Olympics to Olympics. Because that slope allows me to predict what's going to happen next more than any other part of the equation. So I would say the most important factor of a line is the slope. So is it linear? This is an important question, and it tells me if there's a meaningful relationship between my explanatory and response variable. The relationship between explanatory and response is slope. So I'm going to do a 4-step hypothesis test for the slope. So step 1, hypotheses. Step 2, model. Step 3, p-value. And final step will be conclusion. Step 1. While I'm concerned about the slope, and my symbol for the population slope was beta 1. The null hypothesis always has an equals some number, in this case 0. Let's think about what this is telling me. This is saying null hypothesis is I'm claiming that the population slope is equal to 0. In other words, that would tell me that there's no relationship between the variables, that it's flat. So for the null hypothesis, I'm assuming that it is not linear, and I will need evidence to show that a linear relationship exists. And whether that line goes up or down is irrelevant to me. I'm really just wondering if there is any slope whatsoever, if that slope is different than 0. My errors follow a t-distribution, so to do this linear regression test, I'm going to be using a t-model. So I'm going to be doing linear regression, and I'm going to be using t-scores. And I am testing to see if this thing looks like a line. So I'm going to be trying to do something called a linear regression t-test. My degrees of freedom for this linear regression t-test will be the number of points, take away 2 for the degree of freedom for the 2 guesses that I've made. So going back to the Olympic data in the very first page here, and there's a lot going on in that first page, I can count that I have 1, 2, 3, 4, 5, 6. I have 7 points. So my degree of freedom should be 7 minus 2. I should have a DF of 5 as I'm working through this problem. If I know the name of the test, I can find it in the calculator pretty quickly. So in my TI-89, I am in stats list editor. And inside of stats list editor, I'm going to choose the option up at the top for test. So I'm going to go F5 to F6. I'm choosing test. And I'm going to scroll until I see anything that looks related to linear regression. There it is. Linear regression t-test. Great. When I choose linear regression t-test, and I'm going to write down notes, and we'll come back to these notes. I know you can't see them just yet. It is going to ask me where my X values are. I've typed those in list 1. It's going to ask me where my Y values are. I have typed those in list 2. And where it has alternative, do you see how that symbol right there, this is a little bit faint, but that's beta. That beta is for the slope. And I'm testing that it's not equal to 0. So I'm going to leave that as is with a not equal 0. And I'm going to hit enter to calculate. Here's what it gives me. When I did this in my calculator, I ended up getting a t-score of, so I did linear regression t-test, I got a t-score of negative 5.989, and I got a p-value of 0.00186. So I did linear regression t-test, I had my X values were in list 1, my Y values are in list 2, and I got that information. Let's do the same thing on our TI-84. I'm going stat, I'm going test, I'm scrolling down to the bottom, I see linear regression t-test, that's exactly what I want. List 1, list 2, I'm testing that beta is different than 0. I'm calculating. Oh, this gives me my t-score, my p-value. It also gives me down here my slope. That's my negative 0.01597 because that's the b that's next to the x. And it gives me my y-intercept of 41.79255. So this gave me my entire equation of the line still. In fact, if I scroll down, it gives me r and r squared. So out of everything in the calculator that I can possibly do, linear regression t-test, this gives me my line, it gives me r squared, and it tests for linearity to see if this thing is going to be like a line or not like a line. My final step is conclusion. So first step, beta 1 equals 0. Alternative, beta 1 not equals 0. This will always be my null and alternative hypothesis when I'm doing this linear regression test. I'm using a t model. My degree of freedom there is k minus 2. That gave me 5. Note, checking in my calculator, it gave me a degree of freedom of 5, so things are checking up. It gave me a p-value of 0.00186. Conclusion, my p-value is low. If my p-value is low, the null must go. I reject the null hypothesis. I have evidence of a linear relationship. And not only do I have evidence of a linear relationship, with my r squared coming in at around 98% or so, or 87.77% rather, I have evidence of a strong linear relationship. So since my r squared is so large, not only do I have evidence of a line, I have evidence of a strong relationship for that line. I'll be making reasonable predictions. When I did this problem, I didn't actually do anything with that t-distribution. My calculator did it on my behalf. I'm not expecting you to do anything with that t-distribution either, but I just want to do a little bit of some scratch work to verify that some of this stuff is adding up in the way that it should. Let me draw a picture of what's going on. So when I'm testing for linearity, this is sort of what my curve looks like for that curve for the error. So I'm assuming no slope in the center. My null hypothesis is 0. And my calculator gave me a t-score of negative 5.89, 989. And looking at the alternative hypothesis, this is testing for does not equals. So when I shade this thing, I'm going to shade it both left and right. This is a two-tailed test. So if I want to verify this p-value, well, my p-value is going to be twice the size of that left tail. If I want to find how big that left tail is, I can do 2 times the t-CDF for that left side. The left side starts at negative infinity, low value. It goes up to negative 5.989. And my degree of freedom here was 5. So verifying this in my calculator, if I did 2 times t-CDF from negative infinity, negative just whole bunch of 9s, to negative 5.989, and if I had a degree of freedom of 5, I end up getting 0.00186. I had for my p-value 0.00186. So even though we are not looking up these t-scores anymore, my calculator is still doing this work for me. So this is just a double check that I can do. If I think that I might have done something wrong with one of my calculations, I can still use t-scores to verify that this whole thing works the way that it's supposed to work. So this is the idea for linear regression t-test. Those 4 steps again. Step 1, I assume that it's not linear, that there's no slope. Alternative hypothesis, I'm testing that the slope is different than 0. My degree of freedom is 5. I find my p-value using my calculator. It spits it out for me. If my p-value is low, the null must go. If I'm rejecting the null hypothesis, I have evidence of the alternative. I have evidence of a linear relationship. So this was my process for using data, 2-dimensional data, to guess what's going to happen for the future. I want to practice this just a tiny bit more. I'm looking at your second day of notes, and I'm going to continue into the next packet here. I'm not going to do much of this packet because we have all of the key components already. So the first page of your packet just reviews the process that we just went through. So read through this and make sure you really, really understand what's going on there. Second page, I'm just giving you a really small example, and I want to do a test for linearity just to make sure that I understand what's going on. And I'm going to use my TI-84 for this just because it ends up being my easier to read screen. So test for linearity, I want to know if this grid gives me something that looks like a line. Null hypothesis is going to be that my slope is equal to 0. My alternative hypothesis is that my slope is not 0. So null hypothesis is not linear. There's no slope. Alternative hypothesis is that it's linear. For step 2, the model that I'm going to use is I'm going to do a linear regression t-test. Degrees of freedom are going to be the number of points minus 2. I had 1, 2, 3, 4 points. So my degree of freedom is going to be 2. I'm going to go into my calculator to come up with this. So I'm going to go stat test, wherever test is in your calculator, whether that be your F6 or just over to test in your TI-84. And we're going to choose the linear regression t-test option. So stat, and if I go over to test, I have to make sure that I actually type in my numbers first. Otherwise, my calculator has no idea what the heck it's doing. So in list 1, I'm going to type in my x values. And in list 2, I'm going to type in my y values. So list 1 was 1, 2, 3, and 4. List 2 was 4, 6, 8, and 6. I am going to the option for stat. I'm going into test, and I'm going to go to the bottom. So I'm going to go to linear regression t-test, enter. My x values are in list 1, and I corrected those x values. My y values are in list 2. I've corrected those y values. And I am going to calculate to see what I get. Degree of freedom of 2, things are looking pretty good. I'm going to write down everything my calculator gives me. It says y equals a plus bx up at the top. It tells me that my a is 4, my b is 0.8. Scrolling down to the bottom, I have an r squared of 0.40. That is not a great sign. This means that if I use this to make predictions, they're going to be really dodgy predictions. I had a t-score of 1.154. This yielded a p-value of 0.367. So even based off the r-squared, I would never want to use this thing for predictions. It only looks kind of like 40% like a line. Likewise, when I do the test, I get a really large p-value. So when I do the fourth step, the conclusion, if I have a large p-value, if my p is low, the null must go. So this is the opposite. So I am going to fail to reject the null hypothesis. And if I'm failing to reject the null hypothesis, then I do not have evidence that the data table provided here is linear. So I do not have evidence the relationship is linear. In other words, if I were to try to figure out what's going on with the slope, the line's just varying way too much for me to figure out exactly how to use this thing to make predictions. I don't have something stable. I do not have evidence of linearity. If I were to make a confidence interval for the slope, let's see what happens. So in our calculators, where this was a test for slope, if I wanted to make a confidence interval, I'm just going to do a linear regression t. Let's make an interval to try to figure out possible slope values. And I'm going to create a 95% confidence interval for our slope, just to see what the heck happens if I try. So in my calculator, I'm going to where my intervals are, and just like I had linear regression t-test, I'm finding the thing that says linear regression t-interval. My x values are in list 1, great. My y values are in list 2. For confidence level, let's try to be 95% confident. I'm going to calculate. When I do so, I get an interval of negative 2.81 up to 3.781, verifying degree of freedom is still coming in at 2. So I have both negatives and positives to my interval. In other words, 0 is in our interval. And when 0 is in our interval, when we're comparing groups, that tells us that the results are inconclusive. When 0 is in our interval for comparing to proportions, when we're comparing to averages, this told us that we could not tell the difference between the two groups. In this case, if 0 is in the interval, it is possible that the relationship is non-linear. So I shouldn't use this for anything important, because first off, my r squared is 40%, and second off, my confidence interval can't even tell me if the line is going up or down. So how can I expect to make any predictions if I can't even pin that? I want to do one more example of this from start to finish. This will be the last example that I do in a lesson video. I have a huge data set here with drop height and bounce height for bouncy balls. This is from me actually dropping from a set centimeter and then seeing how high it bounced on that meter stick. So I dropped it from 10 centimeters and it bounced 9 and so on. So this is my raw data. I would like you to type this raw data into your calculator. I'm going to pause for a second to give you a chance to do so. And as you do so, I will actually do so as well. So I'm clearing out my list and I'm going to type in these numbers. And I'm going to ask you pretty much every question I could reasonably ask for this data set given our tools thus far in the course. So from this data set, which I have typed into my calculator in list 1 and list 2, here are some of the questions I might be curious about. State the explanatory and response variable. Remember, the explanatory, this is your X variable. This is the thing you control. Y, this is the thing that happens in response. For this example, did I have more control over where I dropped it from or where the thing bounced? While I can't control bounce, I'm not a god when it comes to physics, but I can control where I drop the thing from. So I would say my explanatory is going to be the drop in centimeters. The response, when I drop it in response, it's going to bounce up, and it's going to have some bounce also in centimeters. Determine the line of best fit, calculate R squared, test for linearity. The nice thing is now with my calculator, I can do all of this in one fell swoop. So I'm going to do this a little bit out of order, and I'm going to start with the test of linearity to see if I should even consider finding the equation of the line of the R squared. Because if it's not linear, then why would I want to do these other things at all? So test for linearity, 4 steps. First step, null hypothesis is that it is not linear. Alternative hypothesis is that it is linear. Second step, my model. I am going to be doing a linear regression t-test, so I'm using a t-model. And my degree of freedom is going to be the number of values here. It looked like I had k equals 16 points. So my degree of freedom is k minus 2. I'll have a df of 14 or so. So in my calculator, I'm going to go stat, test, linear regression t-test, and I go down to calculate. This gives me a t-score of 69.4618 or so. And it gives me a p-value of, oh, very cool, e minus 19. So this would be 18 zeros and then a 4. So this is definitely a 0+ kind of situation. Other information that my calculator gives me is it says the line is equal to y equals a plus bx. It says a is equal to 1.43. It says b is equal to 0.799 or so. It gave me, scrolling down further, an r of 0.999 and an r squared of 0.997. So this is the stuff that my calculator gave me. It verified a degree of freedom of 14, so I knew I typed my stuff incorrectly. It gave me a t-score of 69.46. 69 would be like way off the table, right? Because within 2 standard deviations is considered usual. Anything outside of that, it's pretty uncommon to see. So something this large tells me that there's really something going on. In particular, with a p-value of 0+, I reject the null hypothesis at almost any level of significance that you could reasonably choose. If I'm rejecting the null hypothesis, this means I have evidence of something. I have evidence of a linear relation between bounce and drop, or between the drop and the bounce, however you want to phrase that. So how good is this relation? Well, that's what my R squared tells me. My R squared was 0.997, so it looked 99.7% like a line. Not only do I have evidence of a linear relationship, it's a ridiculously strong linear relationship. What does that line look like? Well, y equals a plus bx. Let's fill in those numbers. My a is 1.431 plus my b is 0.799 times x. I've plugged in my a and my b. I'm remembering that lines are supposed to actually look like y hat because they're predictions. So the equation I can use for predictions is y hat is equal to 1.431 plus 0.799x. And I can use this to make predictions. I'm just going to make a single prediction instead of a confidence interval of predictions for this last value. How high will this thing bounce if I drop it from 100 centimeters? So I am predicting, if I plug it in at 100 centimeters, that it should bounce approximately 81.331 centimeters. Now, it's probably not going to be exactly that, and if you're wondering what the errors would look like, well, the errors would be related to that E model, those normal curves that sort of go along the line there. So this is a reasonable prediction, give or take some margin of error for those predictions. We have looked at confidence intervals and hypothesis test for 1 proportions, 2 proportions, and multiple proportions. We've looked at doing confidence intervals and hypothesis test for single averages, matched pair, and 2 independent. We've also looked at doing ANOVA analysis for multiple averages, 3 or more averages. And finally, we compared multiple points in higher dimensions like 2 or 3 or whatever using linear regression. This is still just sort of the surface of some of the stuff that you could do with statistics. Other things that you might want to think about for the future is, where does all this information come from? So taking a survey methods course could be a useful thing if you're looking to do this in your job or in the industry. And the other thing that might be interesting to do as a next step for your research is, how can I use models, or what models can I use when the assumptions are not met? We're kind of dealing with the best case scenarios here, and this might take care of like 87% of the situations that you run into the world. As you learn more, you're just going to fill in more and more of that gap. You will never perfectly know everything, but at least you'll be stronger as a statistician and as a consumer of research. I like 244 because this is a course that's sort of ready out of the box to be used for predictions, and I've really enjoyed being able to take this time and share some of this with you. I hope that you've learned a thing or two throughout these lessons.